Okay, thank you for pulling up this video, and I will appreciate your feedback tomorrow in class on how the video went, what you understood, what you didn't understand. So as we go through this lecture, if you would just make some side notes as you're taking your notes on questions that you have and your thoughts, I'd really appreciate it. Today's lesson is on polynomial functions of higher degree with modeling, and I did figure out how to get rid of the recording icon, by the way. It's a fairly straightforward lesson as it goes back to our talk about polynomials, and I think this will lend itself well for this type of format. First, the cartoon, and I won't skip over it this time. The Born Loser, what's the book, Alvin? The son goes, Advanced Calculus. I thought trigonometry was tough, but wow. And the father goes, hey, kiddo, wait till you get to long division. And I put that in there because we actually are going to get to long division in this unit, but it's going to come up a little bit later. We're going to be dividing polynomials for a reason, and I'll explain when we get there. But the long division, you know, I remember back in 5th grade, it was tough back in 4th and 5th grade, but now looking back, those were the good old days. So what are we doing today? Today we are going to look at the graphs of polynomial functions and specifically the end behavior of polynomial functions. I will stop it after about 15 minutes or 20 minutes of lecture, and so we will not get to the zeros and some of the other topics on here. This is really an interesting area for us, though, because you're going to understand not just the algebra behind polynomial equations, but why the graphs end up looking the way they do with the number of times they cross the x-axis, the number of local minima and maxima. And I think it's going to put together a lot of the pieces of things that we've been talking about, and hopefully it'll be more understandable. So first, some vocabulary. If you've got a polynomial, and we're back to the original definition of polynomial, all of these exponents have to be positive integers. It's basically going to be of the format of some coefficient times a variable raised to some power. But in this case, because it's a polynomial, it could have several monomials in a row, and we designate those with the coefficients a sub n minus 1, all raised to various powers, and this can continue on until you eventually get to a sub 1 times x, and then maybe a constant at the end. So, some vocabulary. We call the variables the a sub n minus 1, a sub 1, a sub 0. Those are all coefficients. A sub 0 actually has a special word. It's called the constant. But the others are all coefficients. Of course, x is the variable, and the power is n. We would say the degree of the entire polynomial is the highest power shown, highest exponent, I should say, and n would be the highest exponent, and so that would be a degree n equation. It's in standard form when the very first term has the highest degree, and we call that term the leading term. And a sub n is the leading coefficient, and I think that pretty well covers the definition. So in your notes, make sure you designate that a sub n minus 1. These are the coefficients. I keep forgetting you can't see me pointing at the board. Those are the coefficients. A sub 0 is the constant term. They're all called terms, but the very first one is the leading term. It determines the degree of the polynomial based on the exponent n, and of course a sub n is the leading coefficient. Okay, enough of the vocabulary. Let's move on. So we've already actually dealt with some polynomials back when we were shifting equations and translating them. So remember, if we had the equation f of x equals x squared, it's just a normal shaped parabola, and I may not be going through the exact coordinates, but you know, so forgive me if it's not exactly going through 1, 1 and 2, 4, but it's pretty close. And we found that we could shift that parabola up. If we added 2, it would shift it up 2. We could shift it left or right by putting a minus 2 before we square. That would shift it right 2 units. And in this case, they have shifted it left 2 units because of the plus 2, up 5 units because of the 5, and then flipped it upside down, reflected it because of the minus sign. And as a result, you're left 2, up 5, but flipped upside down because of the minus sign. So left 2 units, up 5, but rather than going up, it goes down. And that is a case of a polynomial. What we're going to be talking about today, though, is when it's just a simple translation, but what happens when you combine multiple polynomials. So monomials. So for example, if we have the function f of x equals x cubed minus x, I want to predict and show you what the graph will look like before we ever graph it by just considering what does the monomial x cubed look like when it's graphed, what does the monomial minus x look like when it's graphed, and see how those two graphs combine to create the graph x cubed minus x. So if you don't have your graphing calculator, you may want it so that you can see if you make sure that you can use it and get the same graphs. But what we're going to graph first is x cubed. Push the graph button. Again, if you don't have your calculator set up correctly, make sure you press zoom 6 to get back to the standard graph, and that's what x cubed looks like. We can go in and graph f of x equals minus x. Clear that out. Minus x. Hit the graph button. And both of these graphs should look fairly familiar to you. Now, what happens when they're combined? Well, literally what you think. Around 0, we're going to get, you can see that these two graphs are just going to add together, and they're both 0 at 0, so the combined graph will go through 0. But notice that the x cubed graph goes off the charts very quickly. As a matter of fact, by the time we get to x equals 3, 3 cubed is 27, and so when x is 3, 27 is way off the charts up here because it's 3 times 3 times 3. F to the minus f of x equals minus x, on the other hand, when x is 3, we just get a minus 3. And you can start to see that the magnitude of x cubed dominates. It's significantly higher than the magnitude of just minus x. 27 minus 3 is 24. The graph is going to start to appear to look much more like the x cubed graph. Try when x is 100. When x is 100, x cubed actually equals 1 million. And it's a significantly larger number in magnitude than the minus x when x is 100 of just minus 100, and the final answer is 900, 99,900. As you can see, the magnitude of the x cubed just dwarfs the magnitude of the minus x. So we would expect that when you have a very large x or a very small x, like minus 100, you get answers that are much more close, or they're closer to the x cubed than the minus x graph. On the other hand, when x is small, somewhere around 0, 1, 2, then all of a sudden the minus x plays sort of a larger role in what the function looks like. So let's take a look at that graph. I'm going to actually just extend this down a little bit so that you can see the graph on here as well. And I'm going to graph y equals, clear this out, x raised to the 3rd power minus x. Hit the graph button. And you can see that the graph looks pretty close to the x cubed graph. It's just got a little bump in it, if you will, right around 0, where it seems to rise up a little bit and then go down. We can explore what that looks like by zooming in on our graph by changing the window, and we'll set the x min to minus 3, the x max to positive 3, the y min to minus 2, and the y max to plus 2. This will just give us an idea of what the graph looks like when you zoom in on that key part. And I'll pull that over there. And you can see that the graph actually has a local minimum and a local max. Here's our local max. And here's our local min. As a matter of fact, if you were to compare this graph between the local max and the local min and just focus on that segment of the graph, that domain between, say, -1 and +1, or -1/2 and +1/2, it actually more closely resembles the minus x. That is actually very close to f of x equals minus x, because the fact is, when you have x cubed of 1/2, 1/2 times 1/2 times 1/2, it's only an eighth, versus x is 1/2. The 1/2 is the larger in magnitude of the two numbers, and so the graph actually more closely resembles the minus x, f of x equals minus x graph, than it does the x cubed. And that's the nature of what we're going to be studying. We're going to be studying what happens when you combine and you have a polynomial that has several monomial terms, and what is the graph going to look like, and how do each of those terms affect which portion of the graph. And I think you're going to find this really interesting. So if you've got a cubic function, though, there's only so many different shapes that it can take. Basically, if you have the leading coefficient, I'll say a sub 3, so f of x equals a sub 3 x cubed plus some other terms for x squared and x to the first, there are only so many shapes that it'll take, and they'll all basically have the same shape. It could be that there are very few other terms and you get the basic x cubed graph. That chart would look closer to x cubed with no other terms really involved. You could have this, which might be like the graph we just looked like, the function we just looked at, x cubed minus x. Or you could have the entire function flipped upside down, if, for example, if you had minus x cubed, or maybe something that looks like this, minus x cubed plus x. Of course, the constant would shift it up or down. The x squared term would have a different effect, also possibly putting in these local and mins and maxes. But basically, an x cubed function is going to start low, finish high, or start high and finish low if the leading coefficient is negative. We'll look at some more examples coming up. Like the cubic function, if you looked at the x to the fourth, called a quartic function. This is the case where f of x equals some coefficient, a sub 4, x to the fourth, and you might have some other terms. And we can play around with some different graphs, and I think I will here in just a second for you, of what some of those graphs look like. But they either have the basic shape of a parabola, maybe an upside down parabola, but you notice as an x to the fourth or a quartic equation, we can have more activity, more things going on in the graph in between the parabola. We can have an absolute minimum, or a relative max, or a relative min, or all three things, or we could have, if it's upside down with a negative leading coefficient, we could have an absolute max. So let's take a look at before I go on, let's actually take a look at one of these and see what it would look like. For example, if I have x to the fourth power, and we can put in a few other terms and just see what they look like. Minus x cubed plus 2x squared minus 5x plus 2. We could end up with a graph, and I actually haven't graphed this, so I'm not sure what it's going to look like, but these other terms could play a role in defining local and absolute mins and maxes. But the basic function, when we graph this, I can promise you will look like this. It's just a question of if there's any activity in between that causes local min and max. So we'll go right away to this, go back to the y equals. We'll try it out and see how it works. And if it doesn't work, I promise you I will come up with one in class tomorrow that looks great. X raised to the third power plus 2x squared. You can see that what takes the longest on all of these is actually typing them in to your graphing calculator. So I have my function, press the graph button, and actually this one ends up looking, let me do a zoom 6 to get the standard look. It actually ends up looking pretty much like a parabola, and there's not a whole lot of activity. It's just slightly slanted as it's caused by the x cubed function. But you can see that what really drives the shape of the parabola is the leading term, x to the fourth. And it looks like a parabola. It looks like it's just been shifted over and down just a little bit. And you might be expecting this to be shifted up too, but the reason it's not is because of the other terms in there. Where are we on time? So we're just about done with this. So I'll just conclude with a couple of synopsis, and this is where we'll pick up tomorrow in class and with a problem. The basic idea is that with any polynomial, it can cross the x-axis at most n times. In other words, if you have x to the first power, it is only going to cross the x-axis once. And I don't care what line, and that's at the most. It will cross the x-axis once. And so it will have what we call n zeros. On the other hand, if we have a quadratic, we can cross the x-axis twice. And as we saw with our cubic function, we can cross the x-axis actually as many as 3 times. And this is actually where I want to pick up tomorrow in class. So we'll finish up the lecture tomorrow in class, and I'll have an example for you to work in class, but it's been 15 minutes, and I will not take up any of more of your time.